Hello everyone, my name is Paul Costa, and today I'm presenting my big data project, leveraging open weather data for weather optimized tourism and travel planning. This project addresses the challenge of manually comparing weather conditions across multiple destinations by automating the entire process. To achieve this, I built a distributed system on Microsoft Azure. As you can see in the diagram, I utilize a master worker topology. The master node acts as the computational core hosting Kafka and Apache Spark. The worker node is dedicated to storage and visualization running InfluxDB and Grafana. The separation ensures that heavy processing doesn't slow down the user dashboard. The data flows. The data flows through a Kafka architecture pipeline, meaning it is processed entirely as a real-time stream. It consists of 5 stages: integration from the API, buffering via Kafka, processing with Spark streaming, and storage in InfluxDB, and visualization in Grafana, definitely. The conceptually, this project minors the standard data mining workflow. We began by selecting specific global cities, pre-processing the raw JSON to clean it, transforming it using our scoring algorithm, and finally interpreting the result visually to aid decision making. Let's look at the code. For injection, I wrote a Python producer that polls the Open Weather Map API every 60 seconds. A critical feature here is the rate limiting logic. I implemented a 1.1 second sleep interval to strictly adhere to the API free tire limits and avoid being banned. The core intelligence lies in the Spark processing layer. I developed a custom user-defined function that calculates a tourism score from 0 to 10. It penalizes cities from rain, snow, and extreme temperatures and reward clear skies. The final output is the Grafana dashboard. It updates every 2 seconds, providing a mission control view for tourism. It includes a global temperature map, suitability bar gauge, and detailed trend lines. We verify the performance in production, achieving a latency of less than 2 seconds across all 50 cities. To make the data accessible, I use geospatial visualization. The top map shows the suitability matrix, allowing a user to instantly spot safe travel zone in green and blue. The bottom map is a temperature heat map visualizing the current thermal state of the globe. We can also track trends. The time series graph on top shows how the tourism score fluctuate over time, for example, dropping at night falls. User can drill down into specific cities. Here is the view for Paris. Beyond just a score, we provide granular metric uh, like real feel, humidity, and visibility. In these examples, Despite a moderate temperature, the high humidity lowered the score to 2.24. Deployment and CI/CD. To ensure reliability, I didn't just run script manually. I implemented a CI/CD pipeline. This automates the build, test, provisioning, and deployment phases, ensuring that any code pushed to the repository it is automatically verified before running on the cluster. Here is a summary of the technology stack. We used Kafka for streaming, Spark for processing, and InfluxDB for real-time storage, HDFS for historical archivals, and Docker container for portability across our Azure VMs. For Kafka, we configured the weather stream topic with three partitions. This is critical because it allows Spark to read from the topic in parallel, increasing our throughputs. Uh, we also set a retention policy of 7 days to ensure data durability. In Spark, we utilize structured streaming. We configured uh, checkpointing to checkpoint slash weather, which guarantee fault tolerance. If the system crashes, Spark can restart exactly where it left off without losing a single data point. Here is a deeper look at the scoring logic. It's a multi-factor model. We don't just look at rain, we analyze wind speed greater than 15 km per hour and visibility less than 5 km. This creates a truly robust tourism suitability matrix. We implemented a dual write strategy where the InfluxDB store real-time metrics with a 30-day retention for the dashboard. The HDFS stores the data in Packit format for long-term historical analysis. This gives us redundancy and flexibility. So this diagram traces the life of a data point from the API call to the Kafka publish. Kafka processing and finally the Grafana refresh, the total latency is consistently under 2 seconds, making this a true real-time system. Uh, in Grafana, we use a Flux query language. This allows us to perform complex windowed aggregation directly in the dashboard, such as calculating the mean temperature over 10-second windows for smooth visualization. In terms of performance, the system handles uh, an injection rate of 50 cities per minute with a throughput of 1.5 MB per second. Resource utilization remain efficient with CPU usage between 40 to 60%. We utilize a Parquet compression to reduce storage cost by 70%. I overcome several key challenges like API limit, which solves via sleep delays, uh, data consistency, which solves via transactional dual writes, then the latency, which solved by optimizing Spark, micro batch intervals, and the uh, fault tolerance, which solved via checkpointing. Significant business value. It can be used by dynamic adjustment by a tour operator, where weather-based pricing for hotels or predictive modeling for historical trends. We also implemented system health monitoring. We track Kafka log, Spark processing time, and disk usage. If any metric exceed the threshold, like Kafka lag over 1,000 messages, the system trigger an alert. Looking ahead, I planned to integrate machine learning for predictive scoring, expand coverage for 500 plus cities, and develop a mobile app for real time user notification. To summarize, we achieve less than 2 second end-to-end latency. We guarantee 100% system reliability with zero data loss. We successfully scaled to cover 50 plus global city simultaneously. Thank you for your time. This project demonstrates how modern uh, big data tool can solve real world problem in tourism. Uh, I'm happy to answer any question. Write down in the comment section below. Thank you.